There we go. Um, so we've talked about the electronegativity ranging from about 0.9 to 4.1 in the case of fluorine, and why that's so important, because you have the net force of the bond ultimately between those molecules. You start out with repulsion and attraction, and you have a distance, so an interatomic separation called R, and that's our x-axis here. So the attractive forces become less and less and less, and the repulsive forces become less and less and less in total magnitude once you've brought them together into a bonding range. And that bonding range is designated by this R naught, so this sort of minimum separation distance required to form a bond. The net force is the combination of those two, the force of attraction and force of repulsion together. The sum of those two becomes zero, at least at that point of bonding interaction. So that's the force graph. So then we also have the potential energy, and the easiest way to think about this is the potential energy being a high point, and it's like a ball or a sphere trying to roll down a hill. So the ball always wants to roll to a low valley so that it can sit there and stop rolling. So it wants to reduce the total potential energy and minimize that. So you have this balance of attractive and repulsive forces. As those two combine, you reach an E naught, which is a net energy of binding between those two molecules. And I mentioned that this is important because it's important to understand that as you compress those, as you start bringing them physically closer together, as you add a lot more energy again to those, you reduce that net energy and make it easier and easier to break bonds. So this is a principle that you see in many, many, many different materials areas. So it takes some force to raise something out of, like if you were using the ball analogy, it takes some force to raise it out of the dip or valley or depression that it's in. The energy is the same way. You have to input a significant amount of energy in order to break that bond, and if it's at the correct sort of native zero state bond distance, so at an RO and E, so R naught and E naught is the best way to think of that. It's a net energy of binding at a natural separation distance between the two of those. So the ball rolling downhill into an energy well, this is what we call energy wells. It's the same kind of energy well that happens creating difficulty with solar panels and continued production, and lots and lots of different things have interaction limitations because of these energy wells that are formed in these as a function of the atomic separation distance. And in the case of solar cells and things, there's some other factors there as well. But the energy is seeking to reach a minimum, and that's why we're remembering the ball rolling downhill analogy. That's really critically important, and a concept that I can say for sure you guys will be tested on, because that's truly critical to understand the behavior of materials, especially the electrical and magnetic components of those. So not going to turn into a full electromagnetics class, but it's something that you need to know. So an energy balance is a combination of the attractive and repulsive energies, just like the force, the balance of attractive and repulsive forces. So we had talked about ionic bonds being between metals and nonmetals. So the metal is doing the donating of the electron, the nonmetal accepts the electron. And these are things that are typically dissimilar in electronegativities. So magnesium oxide is a combination of the 1s2, 2s2, 2p6, 3s2, and the 1s2, 2s2, 2p4 orbitals. The 3s2 gets added to the oxygen, and so the magnesium takes on a +2 charge. The oxygen takes on a -2 charge, which is where it's happiest because its electron configuration is like neon. Magnesium drops backwards to be like neon, and that's why this is important. So both of them have 10 valence electrons in total. Those are the keys. Is both have stable filled valence shells, and they're much happier at that state. So this ionic bonding is between these positive and negative ions. It has to have electron transfer. If it doesn't have electronic transfer, it's not ionic bonding. Sort of like the whole concept of it doesn't have a tail, it's not a monkey. I think there's a song about that. Of course, I don't actually know if you guys are old enough to know what that is, so that's a whole other issue. +1 in chat if you know what I'm referring to. The large difference in electronegativity that's required is a good example of something like NaCl. So sodium is the unstable metal, chlorine is the unstable nonmetal. They come together with an electron exchange in order to become a cation anion pair. So just like all ionic bonding pairs, cation, there's a couple easy ways to remember that, but I think the best is to think of the cation as the one that has given away its electrons by way of like a cat that comes up and rubs up against you and delivers an electric shock because cats are evil. And you remember the plussy cat face, something that you'll never be able to unsee. So I will pass this down from many, many generations ago. You have a cat face, and you have, let me redo that slightly so that you can remember this, have it seared into your brain forever and ever and ever and ever, because drawing with mice is definitely a thing that people should do. So you have Plussy Cat, and Plussy Cat is evil, and so we'll draw it with fangs because Plussy Cat is evil and delivers an electric shock. Now it looks like Plussy Pig, but you'll get the idea. A couple more fangs in the bottom. There we go. So Plussy Cat. This is why it's easy to remember which one is which, because cats are evil. The anion is taking all those electrons and storing them up in order to stabilize itself. So all of these things are critically important for the behavior of these materials. So what we can do is, let's see, think about the way that ionic bonding happens in ceramics. This is going to become important for the macro scale behaviors that you'll see later. These ionic bonds are very strong because of that exchange. We have Coulombic interaction, which is a lot stronger than simple hydrogen bonding or something like that. But as these materials give up their electrons, in the case of things like calcium fluoride, cesium chloride. Something like salt is not extremely difficult to separate when you put it into water, right? If you put it into water, those ions dissociate fairly readily. But is salt itself is fairly hard. It is a rock and it has to be mined. People don't just dig it out of the mountainside with their fingers. It has to be mined using equipment. So it's a very hard material until you have an interaction with water, and then it simply readily dissolves. So it's a good example of a ceramic-like material because they tend to be very hard. They tend to be very brittle, so they will fracture, just like salt will, right? We have salt grinders for a reason. We don't have salt lightly tap the salt and it disintegrates. Like we have mechanical grinders with geared advantage so that we have enough force to be able to mechanically rip those bonds apart. So they're very strong. You have a, a tactile sense of what this kind of bonding results in, even if you don't fully understand the rest of atomic bonding. That's why we'll come back to this example a number of different times, is you have a sense of what hardness salt has, and it's a good representation of a ceramic. So it's something that does break, it does shatter, but it requires force, and typically it requires either a high shear force, in the case of something like a grinder, or it requires a high impact force, so a very sharp input of energy over a very short span of time because of this, the energy well. You have to deliver that energy spike in a very short amount of time to be able to fill that entire E naught distance between the zero state where they can separate and where bonds are formed. And that's why we have to actually grind salt, is all because of this valence electron shell exchange. So this is something that's important because as these atoms give up their electrons and they become happier in these states, they don't want to move. They want to stay in place unless acted upon by an outside force. So the fact that water put into or poured onto a salt block starts just immediately stripping those atoms off is part of why it's really important to understand the behavior of materials under different conditions. Because if we built bridges out of salt, places that have high moisture in the environment would not have bridges for very long, right? So we have to understand what these materials are going to do in a lot of different kind of environmental contexts. So bonding energy tends to be, for these, somewhere between 600 and 1500 kilojoules per mole. That becomes important when we're trying to break them, but for the stuff that we're doing, we're not building components and applying stresses based on their chemistry exactly. There's some other levels in there. So covalent bonding is critically important because this is a large percentage of the molecules that we interact with on a daily basis have covalent bonding, especially all of the polymers that are involved in your particular caffeine delivery mechanism, whether that's by normal cup, whether that's by bottle, can, etc. Even the cans have a polymer lining typically. So very, very important aspect of daily life. The bonds are determined by these S&P orbitals, and that controls whether or not things are shared or whether things have where the electron is going to be and and what statistical likelihood you're finding the valence electrons in one position or another. So the electronegativities of the atoms in the case of something like H2, hydrogen gas, the electronegativities are the same. So there's two 1s electrons, and they both share with the other hydrogen. So this part is fairly straightforward. It's more interesting in more complicated examples, but it's something that is covalent bonding is directional. So it's only existing between one atom and another atom that participates in this electron sharing. And so covalent molecules have very specific structures, and those electrons fill very specific roles in the orbital regions where the overlap is. So the bonding energy can be anywhere from 100 to 1300 kilojoules per mole. So it's less than the ionic bonding, which is why ceramics are stronger than, for instance, the strongest polymers that you can come up with. The bonding energy is just lower. This is why waxes and things like that on a car surface out in the hot sun, where you have lots of energy being delivered, those polymers tend to have lower bonding energy than ceramics that they're starting to use in coatings now, because the UV component especially is very high energy delivery mechanism. That wavelength has a tendency to disrupt organic molecules. And so waxes and things break down in that UV environment in the sun a lot more quickly. Whereas diamond there, you would think would be the highest bonding energy of all, but it actually isn't. It's somewhere in the mid-range, so about 713 kilojoules per mole. Higher bonding energy doesn't necessarily mean stronger, but the difference is, in the case of diamond, the carbon lattice structure is actually what gives it its strength, not the fact that it's got a higher binding energy. So it's not the tell-all, but it does give you at least some kind of an idea. So a substance can be exceptionally hard without having a very high bonding energy. Metallic bonding is different because it's a sea of electrons. This is part of the reason why these work so well for things like electrical conductors, for instance, is they are sharing in a more group sort of sense, these electrons, and they have much lower bonding energies than some of these covalently bonded molecules. So these have an ion core, and they have a sea of valence electrons. So when you apply a difference in charge from one end to the other, the electrons jump from atom to atom and leave a vacancy, allowing atoms, typically we think of it as going from left to right. So the electrons come in from the left and fill in the holes on the right side as the electrons migrate through. Because they have so many of them available, they tend to be very good conductors. Whereas some of these things in the far left side of the periodic table are not really great conductors by themselves. So secondary bonding. This is typically something like van der Waals interactions, and their energies are a result of things like molecular dipoles that are being formed. So these are important because of how atoms of different sizes and difference in charge will have secondary bonding, but it's a lot lower in strength, something on the order of 10 kilojoules per mole. So it's not strong enough to resist things, but this is in the realm of things like adhesives, for instance, are these kinds of secondary bonding. So not nearly as strong. Like, you don't put a piece of tape on the aluminum and then you start to rip the surface off of the aluminum, typically speaking, right? When you try and peel up the tape. But tape is a good example for you guys to think about the molecules actually involved, where you have secondary bonding. So it's something that can bind stay put even in vibrating environments and things like that, but they don't necessarily have a permanence in bonding. So that's where these secondary interactions come in, and that's like the entire range of adhesives, specifically things like polymer adhesion with secondary bonding. So lots of opportunities for hydrogen bonding just by way of sheer number of molecules, and that's part of how adhesives work the way that they do. So some example substances they give from one of the tables that's in the book. It's not important that you have these memorized. It is important to have a sense of what some of these are. So sodium chloride, magnesium oxide, calcium fluoride, these are different salts that have quite varied bonding energies, but you can see their actual melting temperature. So the melting temperature of salt in dry air, very important there, in dry air is on the order of 800 C. So that's even higher than the melt temperature of aluminum. So down in the metallic bonds, you see 660, which is somewhere in the range of about 600 C is where metals start to become emissive. So in the 340 labs this semester, you'll get to kind of see some examples of this, where the melting temperature for steel is considerably higher. The melting temperature for mercury is minus 39 C. So mercury is, in our experience, almost always in a liquid state. So silver, much higher melt temp at about 960 C. But you see, for instance, the covalent linkage, because of the actual mechanical structure, the melting temperature of diamond is in excess of 3,550 degrees C. So diamond is an incredible material from an industrial use standpoint. This is why it makes really good cutting tools. Silicon carbide is similar. So silicon carbide is a fairly common, carbides and nitrides are pretty common tool coatings. We'll find out later in the semester why that is, has to do with hardness, but it turns out also their melting temperature for silicon carbide, because it's a ceramic. So this is a covalent bond, but it's very strong. Has a binding energy of about 1,230 kilojoules per mole. The van der Waals interactions for gases are very weak. So these are very low melting temperatures. They prefer to be in a vapor phase. Hydrogen bonding, so between things like HF or NH3 ammonia, water, for instance. Did anyone know that water has a melting temperature of 0 C? Curious to know how many of you actually remembered that. So hydrogen fluoride, another good example of having a very low melting temp, so minus 83 C. So all of these are based on what the metallic interactions or what the molecular interactions are doing to determine how those will behave in other applications. So there's a lot of interesting components there. So the ionic bonding is very large. Bond energies, covalent is variable. So there are some instances like diamond where it's very high. There's things like semiconductors and ceramics fall in this case. There are ionic ceramics, and those tend to be very strong. The metallic bonding energy is quite varied. So something like tungsten has a very high binding energy. So again, it works well at a very high temperature because of that high binding energy. and that allows for non-directional interactions. That's why tungsten works really well for filaments, whereas the small bonding energy of mercury makes it not a particularly great metal to use, because a liquid metal is not all that useful. Why they decided to go that route for Terminator, nobody will ever know. You'll have to ask the 80s. So the secondary bonding, especially in between polymers, is the smallest, and that's where especially a lot of adhesives and things happen. All right, so we're going to jump over to start some of chapter 3, but I know there were a couple questions. So almost Curious George reference, very close. So paint is an example of secondary bonding initially, yes. So that's a good question. Paint is an example where you have a start where you have polymer-like secondary bonding at first. You have that first layer deposition where you clean, where you start to coat the metal surface with something that begins to bind to it. There is a chemical reaction that happens because a lot of those paints are, you've heard terms like epoxy or acrylic paints. What that's referring to is the type of polymer base that's used. They're a special category of polymers called resins. And these resins, what they do is they start out in a liquid form and they polymerize, meaning they have some activating agent that's also mixed in with the paint. So if you have paint that's been sitting on a shelf for 150 years, it's probably not actually going to be paint. It will be a solid, because the ionic state of that container will have changed over the course of time, because they have components that want to react together. They also have mixed add-ins that keep the reaction from taking place. So there's a very careful ratio of all of these things that are put into place. As time goes by, those become less and less effective. Polymerization starts, and so this is why paint will tend to dry out and change over the course of time. Or you've picked up an old can of spray paint and it still has pressure, but nothing actually comes out. That's typically what's happened, is you've started to get these clumps of polymerized materials forming. So they bond using secondary bonding to the surface, and then they react and cure. So more and more cross links and things happen, and then you have a very high surface area over which the secondary interactions take place. And if there is, this is part of the reason why, in the case of a panel that hasn't been correctly cleaned, for instance, beforehand. So there were a lot of, especially like GM vehicles in the early 90s that had a metal surface that was not very well cleaned from the factory, and they were trying to use some slightly more environmentally friendly components in their paintwork. They tended to just have sections of their paint peel, and so cars that were not even 3, 4, 5 years old would just have a third of the paint from their hood missing, because there was some small degree of contamination, or there wasn't a good adhesion between those polymers and the raw metal surface. So I think contamination was probably more to blame with that, but that's just an example. So those are important materials properties to understand as well. So yeah, secondary bonding and adhesives is an important part to understand for sure. So let me get this chapter started. And we'll jump into this one. Because I know we don't have a lot of time left, only about a half hour, so we won't be able to do the whole chapter. We'll get through what we can. There we go. All right. So things that we need to focus on for this chapter, this is the stuff that we really need to get to really begin understanding the material behavior. So we're out of the sort of um, hardcore chemistry portion of the class. We'll come back and touch on some of the principles of that later when we're talking about some of the other kinds of material properties. But this will at least give you a foundation for what we're going to get into now, which is the atomic arrangement between crystalline and non-crystalline solids and what that starts to do at the atomic level and how that starts to function. There's some really interesting demos with video that I'll be able to incorporate for this, and it should be very helpful for you guys to get a better understanding of what's going on. So we also want to understand under what circumstances does a material property vary with the measurement direction. So something that you guys have not had to think about yet is why does it matter which direction you're measuring a property, and what does all that stuff even mean? Because this is a whole new world for most of you guys. So we talked about the bonding energy and the typical neighbor bonding energy and the bond length and how that changes as a function of time. There are some different kinds of packing, and in this case, we have not the densest packing. We have just a randomized packing of the atoms. We also have dense or ordered packing, and that is typically at a higher it's typically a higher energy, and so that's what I mean about having a minimized um, interaction distance where you're not actually physically compressing them, and you're not stretching them and ripping them apart. So there's two different places that we are on this energy diagram, and this is part of what we need to understand in terms of how does all this stuff work? How does all this stuff operate? Dense packing tends to have much lower overall energies, and so the magnitude of the energy is greater, but the overall value is lower because it's at that low negative point. So dense ordered packing is a little harder to disrupt than random packing, which makes sense if you guys are have ever been in sort of a crowded room. If it's standing room only, it's really hard for you to physically move through. If you're like one of those atoms, it's very hard for you to physically move through from one end of the room to the other to get to the punch. It's very easy if people are sort of scattered around randomly because you can kind of weave in between some of the gaps and open spaces. Molecules are in this sense not much different, so it'll help you to visualize. So crystalline materials and packing becomes very, very important. So crystalline SiO2. Can anybody tell me in the comments why SiO2 is such an important material to understand? Does anyone know where you guys are? Literally your absolute lives depend on it. You guys being able to breathe every single day. Does anybody have any idea? Whereas SiO2 in common use that you guys are utterly dependent on, like 100 million times worse than somebody hooked on really good drugs. Anybody have any idea? hear crickets. I'm going to need like a sound effect board. Yes. SiO2 is used in beef jerky, also used in shoe boxes and things like that. Yeah. Some people can't live without beef jerky. That's fair. Um, okay. Quartz, good guess. Quartz is a crystalline form of silica, yes, but not quite. A little more rudimentary than that. What's that material? There probably is a small trace amount of silicon in your bones. SiO2 is the chemical formula for sand. It's also the chemical formula for glass. And it is also the chemical formula that is used for, it's used in capacitor, it's used in all sorts of other things. There's silica is the base form used to make all sorts of semiconductors. So almost all semiconductor chips are used making silica. So it's also the chemical formula for glass. So this is a molecule that you guys are utterly dependent on every day. Without it, there would be no Facebook without SiO2. It's interesting as that is to think about. So these atoms are packed in periodic 3D arrays. And this is typical of things like metals, but also many ceramics and even some polymers. Crystalline SiO2 can also be more like some of the non-crystalline materials. So these are ones that have no periodic pattern. So the difference is non-crystalline SiO2 is more flexible. This is similar to the base form for polydimethyl siloxane is one of the examples. So something that is a non-crystalline form, and that's the material that uses or that coats the back of the tempered glass that you guys probably have on many of your phone screens. So that's what actually makes it stick to the glass is non-crystalline SiO2 bonding to the crystalline SiO2 of the phone screen. So again, keeping it a relevant example for you guys to understand how the same material can behave so very differently, depending on whether it's a crystalline arrangement or a non-crystalline arrangement. So the periodic packing allows for complex structures, rapid cooling, and all sorts of things like that, depending on how they are processed. So many ceramics and almost all metals are typically crystalline in nature, and amorphous is your $5 word for non-crystalline. So amorphous is something that we'll use fairly often. Metallic crystal structures are going to be very key to understanding how metals interact and how fault propagation happens, and all of those sorts of things. So we want to understand how can we stack the metal atoms in order to minimize the empty space. So these two examples are 2D layers that can be used to make 3D structures. This is important to understand in order to make sure that you get the right kind of strength for the material that you're using. And the atomic packing becomes very, very important. So the one on the left clearly has less open, empty space than the one on the right. So think about how you would stack ping pong balls in a box or something like that. These metallic crystal structures tend to be densely packed. And the reason for that dense packing is because there's usually only one element present, meaning all of the atoms are the same size. Much less common that the atomic radii are different. So there are some instances like that, but we're not going to get into that now. The metallic bonding is not directional, so nearest neighbor distance tends to be a little bit small, so that it facilitates a lower bond energy. So they're closer together, they can have a lower bond energy, and that also makes metals a little bit more stable overall than some materials. But the electron cloud kind of shields the cores from each other, so they don't really have direct core-core interaction. And these are often going to have the simplest of crystal structures. So we'll take a look at 3 structures to understand what those look like. So we have simple cubic. The low packing density means there's not much that actually has this particular structure. So the simple cubic has quarters of atoms at each corner of a unit. So we'll talk about this. This is a unit square or unit cube of the lattice. This means that they have a coordination number of 6, meaning the nearest neighbors, there are 6 nearest neighbors. And it shows the example of this off to the right here. So you have one above, one below, you have one to the left and right, and you have one before and behind. So you have a total of 6 nearest neighbors. We refer to that as a coordination number. So simple cubic is not too difficult to understand. The atomic packing factor, and this is where it becomes really critical to understand each of these atoms in a unit cell. The atomic packing factor is an efficiency metric that we've come up with to describe how these behave. So it's the volume of the atoms in a unit cell divided by the volume of the unit cell itself. So it's a very simple, efficient metric to use. So the number of atoms in a unit cell, since it's actually 8, I think I said quarters earlier, it's actually 8. So I was thinking of each of these pairs being a quarter, but eighths of an atom times 8. So 8 eighths, meaning 1 atom per unit cell, times the volume, which is 4/3 pi times r, the radius being 0.5 a, whatever value a is. A changes based on which individual atom it is. So you end up with the simplified example here for the unit cell volume, and the 8 eighths is the key thing to understand. So 1 atom total per unit cell. So this volume metric will change only slightly with some other examples, but the atomic packing factor turns out to be 0.52, because regardless of what size the atoms are, the packing efficiency is 0.52, or you can think of it as 52%, meaning 52% of the volume of the cell is occupied. So that's not very high. That leaves a lot of open space. This has led to a number of comedians that have gotten a hold of this and saying things like, well, look, if half of the volume of everything is open space, why can't I pass through walls? The TLDR there is because reasons. That's not exactly how it works. It has to do with those repulsive forces. And without those, you wouldn't be able to stand on the floor that you're standing on, and then you would just fall through to the core of the earth and burn up with a fervent heat, because it's many, 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 many thousands of C at the Earth's core. So yeah, don't ask questions you don't actually want the answer to. The second example, and this is probably where we'll pause for today, is body-centered cubic. So this is where atoms touch each other along the diagonals of the cube. So all of the atoms are identical. The center atom is shaded differently only because it's a whole atom, just to make viewing a little bit clearer. So chrome, tungsten, iron, tantalum, molybdenum, etc., all have these same kind of base body-centered cubic structures. So these structures and things about their coordination numbers, things like that, this is absolutely stuff that we're going to be focusing on for test questions, because they're really critical to use. So the coordination number is 8 because you have a plane of atoms above and below, and there's 4 in the plane above, there's 4 in the plane below the atoms. So the coordination number there being 8. So there's 2 atoms per unit cell, because there's 1 center and then there's 8 eighths again, meaning there's 2 atoms per unit cell. And they like to tell you that they have this 3D visualizer for things, because at one point in time, long before you guys' existence, like 20 years ago, visualizing stuff in 3 dimensions was like a new thing, and they were really excited about it. So that's how long this particular book has been around, to have that many versions of it. Atomic packing factor for body-centered cubic looks like this, and you find this by taking a triangle first of the base, and remembering that the length of the base is a squared on each side. So you have a squared plus a squared equal to this length, which comes out to be the square root of 2a. So 2a squared, square root of that is square root of 2a squared to get this distance. So going back to trig basics. And then on this diagonal, so this is the 2-dimensional slice of this 3-dimensional triangle going diagonally through all of those atoms, we get, again, a squared plus square root of 2a, all of that squared, equals this length. So we solve for that, and then we get square root of 3a as our diagonal distance. So the number of atoms per unit cell is 2. Then we have 4/3 pi r cubed for the volume, because reasons. The r is, in this case, square root of 3a over 4 cubed gives us our volume, and our total volume of the unit cell is a cubed, meaning that we get an atomic packing factor for body-centered cubic of 0.68. So 68% of that space in a unit cell for body-centered cubic is occupied by atoms. So that's considerably higher than 0.52, which is part of the reason why that's the natural state for many types of metals. There's another one that we'll get into a little bit here this next session, that's going to be face-centered cubic, and then we'll talk about some other forms as well, but we're going to focus in on what that looks like. So a lot of other metals, especially things like lead, which tend to be heavier. Those are bigger atoms, weigh a lot more, and they tend to be very, very densely packed, which is why they're heavy in a very small, compact form. It's because of their particular crystalline structure. Silver and gold are also in that category. So there's a lot of examples. So these are really great metal conductors, typically. So we don't see iron and tungsten and some of those in really, really great metal conductors, but nickel, platinum, silver, gold, copper, aluminum, all of these are really great electrical conductors. because of their immediate proximity, and we'll find out ultimately because of their packing efficiency. So we will stop there for today. One other question. So A is not the diameter being used there. So A is the length of a side of the unit cell. And so A is not necessarily, in the case of the body-centered cubic that we saw, it's, in the case of the body-centered cubic, the body-centered cubic, A is less, or actually greater than, the diameter of the atom. In the case of the face-centered cubic, A is proportional to the diameter of the atom because of the way the packing works. So A is not directly associated with the radius of the atom itself, but because the A falls out in the atomic packing factor calculation, we don't have to worry about what that exact value is. All right, so as we go to close out for today, because I know everybody's going to be scrambling very shortly to get to classes, any additional questions